So I begin by recalling some basic definitions we saw last time. So suppose that x is a continuous random variable with the density function fx of x, which we just sometimes write simply fx. Okay. Then expectation was defined as integral minus infinity to infinity x fx dx. Okay. And we stated one lemma on expectation of gx is equal to integral minus infinity or well or g for suitable g. So let's not worry so much about this. For which right hand side makes sense and is finite. So I'll just simply say exists. And we want to prove that today for assuming that. So we prove this assuming that g of x is greater than or equal to 0. We may assume that g of x is also continuous, integrable, so on and so forth. So, okay, so this is the basic assumption. And so, before we prove this, we need another lemma. So, I just say using the following lemma. Okay, so suppose that so fx, the density function, is 0 for all x less than or equal to 0. Okay, or less than 0, let us say. Okay. Then expectation of x is equal to integral 0 to infinity 1 minus fx dx, where of course capital Fx is the where fx is the distribution function. Of x. So what is that? Fx is probability that x is less than or equal to x. Yeah. Okay. So how do we prove this? So you just compute expectation of x. Maybe you compute the other way around. Is equal to integral uh, 0 to infinity x fx dx, because of our assumption on f, right? Density function is identically 0 for values of x below 0. Now let's just do this integral 0 to infinity 1 minus fx dx is equal to integral 0 to infinity uh, 1 minus this thing is probability of x bigger than x. Okay, and probability of x bigger than x, you can rewrite it, is actually again, uh, yeah, so this is y bigger than or equal to y equals 0, no, x to, rewrite it as an integral, okay? Y equals x to infinity, write the density function fx dx. Sorry, fy dy, and then dx. So this quantity is exactly this, yeah. By just the that, I mean, we are just computing probability of this given the density function, okay? And now that's equal to, so you draw this region, the only region that is relevant. So let me draw this picture here. F is 0 for values of this below this, and then this line is relevant, is x-axis, y-axis, okay? And this line is the line y equals x. So what is this? So for a fixed dx, okay, you are integrating this way from x to infinity. And as x varies from 0 to infinity, that means you are just doing integration over this region. Okay, but now change the order of integration and write here, we will write the limits in a minute. So write fy dx dy. So first do the integration with respect to x. That goes from where to where? 0 to y. 0 to y. And then from here, y goes from 0 to infinity. Uh, this is values of x, okay? And y goes from 0 to infinity. So that's integral 0 to infinity. So fy is constant when you integrate it with respect to x. So you get, yeah, fy, and then you plug in. So there's just you get x between the value 0 to y, and when you evaluate it, so should I write that? Okay, I write it between the value 0 to y, and then dy. This is exactly integral 0 to infinity y dy, y fy dy, which is of course expectation of capital X. Except that instead of, yeah, I mean variable, how does it matter? It's so I have to, okay. Hmm. Now, yeah, uh, so we assume, so proof of the first lemma, so lemma 1. So proof of lemma 1, you can do it now very easily, because g of x Okay. So assuming since g of x is greater than or equal to 0. Okay. Mm, you see, yeah, let me. Now, what do you want to prove? The expectation of g of x. Hmm. Okay. Yeah, yeah. So we had to do this following thing. Yeah. Hmm. Yeah, maybe. Just once again. Let me see what you need to do in this. Uh, just forgot. So let me look at. Hmm. Yeah. Yeah. So g of x. Okay. Hmm. So where is that? Can't find my. So I think we just have to compute it. So there's some minor thing I need to say, but let's just do this calculation. I think it will come out right. Expectation of g of round bracket x is by definition integral minus infinity to infinity. Yeah, x times. Okay. Next times, I think this is what we'll get. Next times probability of, I think we had to write like this, g of x. Just apply the definition, that's all I think. G of x is bigger than or equal to x. Okay. But of course, this is empty set if since g of x is bigger than or equal to 0, so integral 0 to,
Sir, why are we taking it greater than or equal to x?
sorry. Uh, hmm, hmm. Yeah, the density function of g of x. Okay. No. Okay. So first of all, okay, this is, sorry, I just got a little distracted. Let me say that once again. Uh, want to make this just a very simple matter, but since g of x is the same, let us just compute the function. So consider. I want to say that the density function of g of x. Okay, so consider probability of g of x less than or equal to some value a, or a less than 0. Now this is equal to, so this is probability of the set, okay, set of all omega such that g of x of omega is less than or equal to a, correct? But this value, whatever it is, g of some value is less than or equal to a and a less than 0 means that this is an empty set. Probability of the empty set, which is 0. Okay. So g of x has density function uh, which is greater than or equal to 0, which vanishes, yeah, which vanishes for x less than or equal to vanish. Okay, let me just because I don't want to use x, vanishes. Uh, no, which is correct way to say that is uh, the density function, yeah, which vanishes identically, vanishes. So vanishes for x less than or equal in x less than 0. Okay, I think that's the right one. Therefore, the lemma is applicable. So expectation of g of x is equal to the integral 1 minus probability of g of x bigger than x or bigger than or equal to x, it doesn't matter. Yeah. So this is what we proved just now. Okay. So 1 minus the distribution function. Yeah, 1 minus f of x. But this is for x, and then x is bigger than or equal to x has density function satisfying this. So in the place of x, you apply it for g of x. Because just now I showed you g of x has density function which is vanishing for values of x below 0. That's what we just now checked. Therefore, the lemma is applicable. So here let me say by lemma 2. This is all lemma 2. And now rest of the thing is calculation. Therefore, expectation of g of
Sir,
x.
it is 1 minus the distribution function of g of x, right?
Yeah. Sorry, here it is less than or equal to. Sorry, thanks. Yeah. So this is less than or equal to, and that is equal to integral 0 to infinity probability of g of x less than or now I can write bigger than or equal to x. Yeah, that's what I wanted actually, bigger than or equal to x, but there's no 1 minus now. So this you rewrite as integral 0 to infinity. Uh, so so g of x, so you write this probability of the set, okay, of all w such that g of x, so g of x w, so okay, uh, g of t is see, in other words, this g of t is bigger than or equal to x, sorry, little x, where t is equal to t is equal to xw, x of w. Yeah, it's hardly, I think I'm taking too much time on doing this. So, okay, so let us just try and understand this set. That's where everything lies. So, no, I left out something. This is probability. W. So this, we have to do something here. So you see, uh, this set is what we need to understand. G of x is bigger than or equal. So set of all W, such that Gx of W, omega, whatever, of W, omega, is bigger than or equal to x. Okay. Uh, there will be another integral coming. That's what I'm trying to get. So this is equal to uh, hmm, union over. Let us write this uh, set Bt. T is bigger than or equal to x, where B of t is equal to set of all yeah, it's a simple matter. I forgot this. I, hmm. So let me just hmm, hmm. So this is no. Okay, I am sorry. I got thoroughly confused about this. So, but it's a very hmm. The idea is to rewrite this as an integral over a certain set, and that set is given by this g of. So we need to write the probability of this, right? Probability of this. Let us just write that 0 to infinity, and here we write, see, something bigger than or equal to x. Now write the density function, okay? F of density function for x, I suppose. Hmm. Hmm. F of x. See this. Uh, yeah, that's the main thing. So okay, let me just. I wanted to say it right way, but I'm not able to say it. This is the set we are interested in. G of x is bigger than or equal to x. Okay, GW. Set of all W such that G of XW. We need a notation. XW is equal to T, so that G of T is equal to, yeah, so this is X equals T. Hmm. bigger than or equal to x, and this is all those w. This is the set where we write xt. Hmm. So this it should be possible to write it as something integral. Hmm. Some x to something here. What is that something? Sorry, I completely got. Yeah, so let me. Now I'll look at the book and then tell you because I have scribbled something in my notes and not able to get help out of it. So I will just look at the book and tell you. Okay. So okay. So this is the set y such that b. So I don't. I should have written t such that. Let me write this. Ah. So this is from x equal to 0 to infinity. Okay, let me say try once again. Yes. So I'm going to let us I try and understand it. I thought I understood it. And obviously made some blunder. Let me do this. It's all right. Yeah. So let us just compute what this is. This is all that we need to do. The probability of what is there in the integration. Probability of g of x is bigger than or equal to x. And one writes this in this particular fashion. So write y such that, uh, so this is the region B is equal to such that b of x, g of x, g of y is bigger than or equal to x. Hmm. Then this is integral over y. So integral over this b. Okay. So whatever I was writing t x omega, that is x omega is called y, which is why I got really confused. So this is just write this as integral over b. Uh, yeah, f of y dy. Okay, this is exactly equal to this because this is what I call this t. Maybe we can just still call it t. Then it would be okay. So let's just call this y. Then what we are not this, but what is inside. So you see, this is set. What is this y? Little y corresponds to x of omega. X omega, you call it little y. I called it something. Okay, so now this is all those y. Okay, that is probability of all those omega such that when you compute g of that, that is bigger than or equal to x. So that's exactly this set. And the important thing is this mm, probability is integration over this set B. Okay, this is a subset of real numbers, and your assumptions about your G is exactly to say that this is a set over which you can make integration. So it could be an interval or union of intervals or something in the Borel sigma ring, sigma field. So this is the crucial point. Okay, once you write it like this, uh, then you can substitute that in here, and yeah, now we can get back to this one. So here, rewrite this as integral 0 to g of y. Okay, uh, not g of y. So let me not write in this step, but next step. This is some set B. We don't know what it is, but we can change the order of integration and then do it easily. So therefore, this one, this integral becomes equal to integral. So I can write here 0 to, the first time I just copied this down, which is what I struggled to write because I had this y and t and everything mixed up. Dy times uh, dx. And now this integration is much simpler if you first do it with respect to x and then do it with respect to y. Okay, so when you do that, you get integral 0 to g of y. This is value x equals 0 to x equals g of y, and then y goes from 0 to infinity, and uh, yeah, so you have fy uh, dx dy. Okay, now this fy dx dy, f is like constant like before, so this now is integral y equals 0 to infinity, fy comes out, and now this is a constant, so you just integrate it, you get x between 0 and g of y, so that becomes g of y dy. So, okay, I really struggled to write this as an integration, this one as an integration, and the right way to, I got really confused because x of omega is called y. In my mind, I was always thinking x of omega is x, and sorry, I made a mess. But I hope that you see that this is the important thing to realize. Once you do this step, next step is fairly routine. You just change the order of integration and be done with it. So this is a crucial step, and this is where, sorry, I got myself a little confused. So please go over it. It's actually a simple matter. I don't know why I struggled so much, but sorry, I confused you. But go over it at home at leisure. You will understand it. Okay. Yeah, I spent a lot of half an hour, I think, doing this. Now let me get back to what else I wanted to do. I have to say these things. Yes. So, like I said, moments. So now it makes sense. Now the definition of moments, higher moments, uh, is justified, is given by. So uh, expectation of x power k. This is something I wrote, but this time now it is justified because this is like g of capital X, which is of course x power k f of x dx. Although we did this only for positive functions, this can be extended also to functions which are not necessarily positive. G of x need not be positive, and yet this is valid, and that's left out as an exercise. So, yeah. Okay, so this is 0 minus infinity to infinity. Okay. And that comment is relevant because this k can be positive or negative. Okay, fine. All right. So is the next thing I wanted to say. Always you have to say if it exists. Okay. So I want to give an example where expectation itself doesn't exist. So example, consider the Cauchy distribution. Consider the random variable. What is it? Um, yeah, x with density function 1 by pi times 1 by 1 plus x square. Okay, so just let us just check that this is indeed okay, because so minus infinity infinity dx by 1 plus x square is equal to 2 times integral 0 to infinity dx by 1 plus x square, and that is tan inverse, yeah, 2 times tan inverse of x between 0 and infinity, and you get 2 times pi by 2, which is equal to pi, and that's why this is a density function. So this indeed gives you density function. It satisfies all the conditions for it to be a density function. Now compute expectation of x is integral minus infinity to infinity x dx by 1 plus x square. Now you can check that this doesn't exist. So you might be tempted to think that, this is an odd function, and then you are integrating minus n to plus n, where anyway, so you can think that it has to be 0, but we never. So if you split it on the other hand, you can split it on the other hand, then write so minus infinity to 0 x by 1 plus x square. Okay, so let's, yeah, so you see, on this side you are going to get something like uh, integral 0 to infinity. You write like this: 1 plus x square dx. Now this turns out to be negative infinity, and this turns out to be plus infinity. You never can associate a meaning for this. So this leads to minus infinity plus infinity, to which we cannot associate any meaning. So doesn't exist. Okay, so let's move on. Uh, there are other ways of, okay, so let me not spend too much time on this. So this is another reason you have to always worry when you write expectation whether it exists or not. Okay, I will work out some more problems involving continuous random variables, but let us do some basic examples. So important examples of continuous random variables. Okay, so this is one exponential random variable. So here, this is x with parameter lambda. Lambda is positive, so you just write the density function has density density function f of x is equal to, yeah, I write that. Just 1 minute. Copy it down. Now this is okay. Some basically, yeah. With density function, instead of density function, okay, I need to look at the book. Let me write that. Yeah. So instead of density function, the function that is given is the distribution function, from which you can also write down the density function. But distribution function fxt uh, 1 minus e power lambda times t. There's some some lambda x or x positive lambda. Okay, I don't t here. Fine. Okay, t is there's a minus lambda here. I wrote lambda positive, so I should write minus lambda t. Okay, and t is bigger than or equal to 0. Yeah, so notice that yeah, you can actually uh, find out the density function by just differentiation. F of t is equal to, just take the derivative of this, which is lambda e power minus lambda t. Okay, all right. So this function appears in a very interesting manner. So from what we call the geometric, start with the geometric distribution. What am I doing in terms of time? Okay. Consider the geometric distribution. Distribution. So where you have with parameter p. Parameter p. So what happens is the following. So what is that? That is geometric distribution takes values k. Probability of x equals k is equal to 1 minus p power. Well, actually, this is p times 1 minus x power p whole power k minus 1. Therefore, if you look at probability that x is strictly bigger than k, okay, so this is, well, you can just do this sum, or you can just take 1 minus p of this and simplify it, you get 1 minus p power k. So this is the probability waiting time, and k units waiting time of k units of time, yeah, uh, before the first success. So what does it mean? So you imagine this experiment where you have a coin, you toss it repeatedly until you get time, until you get your first head. So how long do you have to wait? Hmm, waiting time for the first success, probability of that, uh, so is exactly equal to this. Okay, so this is the interpretation. So this is like probability of waiting time equals k. Probability that uh, waiting time equals k. Better not to write this equal to k now because I already introduced this. So now imagine that your, the time you. So now we are going to replace discrete time by continuous time. Okay. So one way to do that is you keep flipping the coin, tossing the coin at time intervals of length delta. Okay. And now uh, you ask. Uh, yeah, so you keep so success, so time for successive flips will be delta. So in one in t units of time, how many times you will have flipped? That's the question. So uh, you ask this again, waiting. So ask for probability of waiting time equals t when you flip, when you toss a coin at time intervals of uh, duration, time intervals of delta units. Okay. So this depends on the number of times you will flip. Let k equals number of flips or tosses in t time t. So that's equal to, so okay. K is equal to t by delta or k delta 50. So you are interested in probability of waiting time equals t units, or waiting time bigger than or equal to t units before the first success. Okay, t units your first success is equal to same thing. So number of flips that you have made is 1 minus p power k. Yeah, k, because you have made k flips during that time. So 1 minus p whole power, in the place of k you write t by delta. So now what you do is allow delta to go to 0, P also to go to 0, such that, so one of the two I keep forgetting. So I suppose, yeah, I can't hear properly, such that, so let me write here. Uh, so it's P by delta. P by delta is equal to lambda. No, delta by P is equal to lambda. I don't know. Delta by P is lambda. Now, what do you get? So this probability then becomes 1 minus, in the place of P you put delta by lambda. Uh, P is equal to delta by lambda whole power T by delta. And you take limit when so take limit delta goes to 0, this approaches 1 minus delta by lambda whole power. So I write this as T lambda whole power. Okay, put the T also outside. Now this goes to e power minus lambda t. Therefore, waiting time the waiting time random variable, that is this, that the distribution of W, density of W. Can you mute yourself, please? I'm not able to hear. Just it's coming to me. Density of W.
You're not missing on anything. Fine, you are.
This is all I wanted to say. So this is a very simple interpretation. When you have your waiting time distribution from going from discrete random variable to continuous random variable in such a manner that delta by p or delta approaches lambda times p, but p goes to 0, lambda goes to p, delta goes to 0, p also goes to 0. In this case, it approaches uh, the continuous random variable with exponential distribution. Okay, so the next is I want to discuss this important distribution called normal distribution. Yeah, so uh, first the standard normal distribution. Okay, let us do this. Let y be the distribution, sorry, random variable with density fy of y is equal to 1 by root 2 pi sigma. Sigma I put here, uh, exponential minus y by mu by 2 sigma. Mhm. So this is the exponential or normal distribution sigma square, 2 sigma square here. Okay, it's called the uh, so this is indeed a density, indeed a density. Okay, so we need to check that. I'll verify that a little later. Uh, the mean, this has mean mu and uh, variance sigma sigma square. Okay, so this is the, and of course we assume sigma is positive. Otherwise, if sigma is negative, this cannot be a density. Sigma is positive. Okay, mu could be zero or anything. It doesn't matter. All right. How do we? Yeah. So the standard normal distribution is one such that, so is a one such that mu is equal to 0 and sigma is equal to 1. That is, as distribution, as density. Uh, yeah, so let us do this. F of x is equal to 1 by square root of 2 pi integral, not integral, sorry, e power minus x square by 2. Okay. Uh, Let us check that. So, um, so expectation of, you can do either one, it doesn't really matter. Expectation of this. Okay, so how is, I want to say the following thing. I mean, just because you rephrased it using a certain specific value for the parameters, it doesn't necessarily mean that there's a simple relationship between y and x. So normal random variable. So suppose that y is the, so let us make a notation here. So we will write this as y is equal to n. I know can imagine some sigma mu or mu sigma square. I think notations. Okay. Y is the normal variate. Y is equal to n mu sigma square. Then x is equal to, so just do this, y minus mu by sigma square. You can check that as mean equals 0 and variance equal to 1. This is trivial to check, okay, by simple properties of mean and variance or expectation and variance. In fact, x is equal to m01. Okay, so that's the main thing. So the normal variate, the standard normal variate is just got from the more general one by just shift and scaling. Okay, so this is all there is. Therefore, it is enough to compute. Okay, after you verify this, uh, so let us compute the mean for standard normal variate n01. Well, what do I mean by that? So just look at this integral minus infinity to infinity x times. So there's a 1 by root 2 pi x times e power minus x square by 2 dx. But this is an odd function. Yeah, so okay, let's not rush to the thing. It could be like a Cauchy and then maybe it becomes infinite and so on. But if it is finite, definitely it is 0. But you can make a very simple substitution, put x square equal to t. Then 2x dx, 2x, 2x dx becomes dt. And so this becomes equal to integral. Okay, so here again, we cannot do this unless you write. Okay, so requires a little explanation, I suppose. Okay, so I can only write it after I do this. No. So there's some, yeah, if you do the same trick for that Cauchy, then you will get 0. But so it requires some justification. Uh, yeah, well, okay, so I think the easiest way is to expand it in power series and simplify and so on. Uh, that may give the answer, but sorry. So I'm not able to give a very rigorous proof at this moment. But if you believe that it exists, then it is of course 0 because this is odd function. Uh,
Also, computation won't take a while. Computation, if that is f minus, I mean, d of minus x squared by 2 is x. So just substituting minus x squared by 2 equal to t. That is e power t dt.
yeah, but so
Then
x square by 2. So wait a second. Suppose you put this.
yeah. So this is just a
Maybe,
minus infinite
maybe
to
that's
infinite.
okay. Yeah, I suppose it's just okay.
For
No,
this case, it is
yeah. No, just okay. It doesn't okay. Put x square equal to t. I suppose that's okay. No, I just unnecessarily panic. Maybe 2x dx becomes dt. But you have to split it into two integrals just out of abundant caution. So this write it like this. I don't know. Maybe this is not required. I'm trying to be uh, very cautious here. Perhaps it's okay to do this. No, this step is okay, absolutely okay, no problem. If it exists at all, this is okay. But once you do this for each one of them separately and then do this, then it will become e power, uh, skipping a step, I suppose. This becomes, uh, So even maybe 2 times integral. Here x is negative, so this direction changes and so on. Yeah. Can I put when x is negative? Okay, this is all right. Uh, x has to be written as minus root of t. But maybe that is not required. But dx dt, yeah, I suppose it's okay as such. Minus infinity. But t always takes positive values. So some explanation is needed why this becomes e power minus t. One should not do this blindly. T by 2 here. And this is 1 by 2. This is 1 by 2 here. That doesn't bother me so much, but I suppose this also is this. Ah, yeah. So here minus t by 2, but t, this is plus, I suppose. When x ranges from here to here, there's a plus sign, and here there's a minus sign. But then I think that this should be okay. 0 to infinity. And then e power. So this is again e power t by 2 minus t by 2 dt. And this is 0. Because, yeah, the crucial point is as x ranges in this taking negative values, but x square always takes positive values, and that is indicated by the statement that I have 0 to this. But this exists by itself, and this also exists by itself separately, and that cancels. That is the main thing. It is not like in the case of Cauchy. See, one has to be careful. You just cannot blindly do all this manipulation. Now, at least you have to realize that it is not correct to do that. If you argued in the case of Cauchy distribution, you could have just said, okay, that's 0 because I am doing integration minus infinity to infinity of an odd function. You just cannot do that. You have to be careful. You have to convince yourself that after you break up also individually, they make sense, and then there is a cancellation. Because that makes no sense, and it's not going to be 0. I think I will have time for one more. Uh, yeah. Okay, let's. I have about 5 minutes. Let me just convince you that f of x is equal to 1 by root 2 pi integral e power minus x square by 2 is a density. So in order to do that, I need to evaluate minus infinity to infinity e power minus x square by 2 dx. This is equal to 2 times integral 0 to infinity e power minus x square by 2. I don't know if it helps to do this way. Never mind. So, okay. Yeah, so now you see you have root 2 pi. You are going to get something involving root 2 pi, right? Better to square this. So I take I is equal to this, then I square is equal to integral minus, so maybe I need not have written this step. Let's just write this. E power minus x squared by 2 dx times integral minus infinity infinity. This is a trick that you just make use of, and it becomes very handy. This is equal to integral. What have you gained? E power minus x square plus y square by 2 dx dy minus infinity to plus infinity. But now use polar coordinates and make a change of variables. So d put so polar coordinates. I'll write quickly. Dx dy is equal to r dr d theta, and this then becomes integral. Well, r is equal to 0 to infinity. Uh, yeah, and theta 0 to 2 pi. Okay, e power minus r square by 2 dr d theta. Okay, this becomes 2 pi integral 0 to, sorry, I made a mistake here also. R dr d theta. We left out that. Without that r, it would be useless for us. Because of this r, it's easy to integrate. Okay, so first to integrate with respect to theta, I already got this 2 pi, and now you can do this at home. Minus r square by 2 dr 0 to infinity. This becomes, I'll just do it quickly, e power something that involves minus r. Okay, maybe some fudging, I think it is just minus r. And you do that between 0 and infinity, you get 2 pi. So therefore, I square is 2 pi, and I is positive, therefore I is square plus square root of 2 pi. Okay, I think I'll stop here. We'll continue in the next lecture. Sorry,